So when we're looking at light waves being given off from these excited electrons, we should mention some characteristics or properties of waves. And this may all be familiar to you. You may have talked about this back in the day, physical science, biophys. This is good stuff. Do you remember the properties of a wave? We classify waves according to their frequency and their wavelength. The wavelength being the distance, either peak to peak or trough to trough, symbolized by this Greek lambda. And here it says measured in units of meters. We should make note, this may also be in units of nanometers. And you have to be a little careful. Watch within the problem if the wavelength is in meters or nanometers. And we may remember that 1 nanometer is a very small fraction of a meter, 10 to the negative 9th meters. Or we could say it would take 10 to the positive 9th nanometers to make 1 meter. Unfortunately, that is not a conversion that's given to in the AP packet. But if your wavelength is given in nanometers, you're going to eventually need to convert that, which we'll look at in the next video. So this may be something that you'd want to put in your memory. The frequency is the waves per cycle, or the number of waves per unit of time. It's usually measured in cycles per second, which could look like 1 over seconds, or maybe seconds to the negative first. Or I think the AP packet just has an S to the negative first. 1 over S would be seconds. You might also see the unit hertz. I think there's a homework problem that talks about hertz. Those would all be equivalent. It's cycles per second, symbolized with the Greek letter nu. The other variable that we'll be looking at is the speed. And we should make note that all electromagnetic radiation travels at the same speed, the speed of light. We'll do a little demo in class to kind of get a visual of why all electromagnetic radiation travels at the same speed. The speed of light is given to you in your AP packet, so you don't have to memorize it. It's a little bit different. In the packet, it'll be listed as 2.998 times 10 to the 8th, and they'll list it as meter second to the negative first, which is meters per second, which makes sense. This is a speed. So again, if you're doing homework problems, use what's in the AP package. You might as well get used to it. But again, you don't have to memorize it. It's in the very first section on atomic structure. We might remember that short wavelengths have higher frequencies, and this would be a higher energy wave. Longer wavelengths have lower frequencies and thus carry lower energy. So we're saying that all waves travel at the same speed, but they do not carry the same amount of energy. And so if you're a visual person, this is what you might picture for waves. The frequency is the amount of waves per time. So we're looking at 1 second's time. My red wave has 4 cycles per second, or they're calling this 4 hertz. And my green wave has 8 hertz, or 8 cycles per second. My wavelength is the distance from either peak to peak or trough to trough. So obviously with this red wave, I've got a longer wavelength, so this would be lower energy. I'm assuming that's why they made it red. And so this green one would, technically green is kind of a moderate energy level, but it's higher than red. So here I've got a shorter wavelength, which is why I have a higher frequency. So these two are indirectly proportional. If I have a lower wavelength or shorter wavelength, it's a higher energy wave or a higher frequency wave. Let's put this in as higher energy. Higher energy. And we'll look at this inversely proportional relationship on the next video with a really easy equation.